Hello students, in this video we will discuss the topic of differentiability and partial derivatives. So let us firstly start with the topic of partial derivative. So firstly we define what is the partial derivative of a function. Suppose that if z is a function of x and y, z is a function of x and y. For any fixed value of y, let y equal to y naught be the fixed value of y, be any fixed value of y. Then f of x y naught, because I fixed the value of y, so it means that now y naught is treated as a constant. So f of x y naught is considered as a function of x alone. Now it's considered as a function of x alone. Function of x alone. So now if we want to make changes, partial increment in that particular function, then in that case we can represent it as delta x. We are making small increment in the direction of x. It can be represented as f of x plus delta x y naught minus f of x y naught. This is called partial increment in the direction of x only. So on the basis of that, we can define the partial derivative of z with respect to x as, so curly z upon curly x. This is obtained by applying limit delta x approaches to 0, f of x plus delta x y naught minus f of x y naught upon delta x. So this is the partial derivative of z with respect to x. So basically, when we define the partial derivative of the function, when we are differentiating our function with respect to one of the variable, we are treating other variable as a constant, right? So similarly, if we are considering x equal to x not be any fixed value of x, let x equal to x not be any fixed value of x, be any fixed value of x, then we can consider f of x naught y is a function of y alone, is a function of y alone, right? So in that case, if we consider the small increment in the direction of y, it is given by f of x naught y plus delta y minus f of x naught y. Now this is the partial increment of z with respect to y. So on the basis of that, we can define the partial derivative of z with respect to y as limit delta y tends to 0, f of x naught y plus delta y minus f of x naught y upon delta y. Okay, so on the basis of that, we can also define the partial derivative of a function at a point. So suppose that I want to find out the partial derivative of the function at the point AB. So because I want to find out partial derivative function with respect to x at the point AB, so it means that we are making variation in the x coordinate only and y is treated as a fixed constant. So in that case, it can be considered as f of the x coordinate is a, so it is a plus delta x b minus f of ab upon delta x. And if I consider curly f upon curly y at the point AB, then this can be calculated as limit delta y tends to 0, f of a b plus delta y minus f of ab upon delta y. Basically, if we find out partial derivative with respect to x, so at any point, it means that in that case, if we are trying to find out partial derivative with respect to x, we are treating y as constant. So in this case, the y, the coordinate point is B only. So we are not making any changes in B. We are making variation only in the x coordinate. That is at the point A. So we are considering the neighborhood of a point A only. F of A plus delta x minus f of AB upon delta x. And if we want to find out partial derivative function with respect to y at the point AB, then according to the definition, in this case, A is fixed constant. So we are making variation in the B coordinate only. So it is f of A b plus delta y minus f of AB upon delta y. So this is the definition of the partial derivative of the function with respect to x and with respect to y at a point AB. So in other words, if I simply want to differentiate my function partially with respect to one of the variable, the simple concern is in that case we are treating only that variable as a variable with which we are differentiating our function, and as whole variable they are treated as constant. For example, suppose that we are considering z is a function of x and y, where I'm considering f of x y as say x square plus y square, right? So if I want to differentiate my function with respect to x, so in this case I'm treating only x as a variable, y is treated as a constant. So in this case we can denote it like in this way also. Okay, so if we are differentiating f with respect to x, this is a partial derivative. Okay, so in this case we are considering only x as our variable, so we are considering y as a fixed constant. So in that case the derivative of x square, I differentiate it with respect to x, then the derivative of x square is 2x and the derivative of y square is 0, because here y is treated as constant. In this case y is treated as a constant. So that's the reason the derivative, we know that the derivative of a constant is 0. So that's the reason derivative of y square is 0. So it, what does it mean? Curly f upon curly x, constant y, its value comes out to be 2x only, right? Similarly, if we differentiate function with respect to y, in that case we are treating x as a constant. So what does it mean? It is curly by curly x of x square plus y square. Sorry, we are differentiating with respect to y, so it is curly by curly y, right, of x square plus y square. So it is curly by curly y of x square plus curly by curly y of y square. So in that case, the derivative of x square with respect to y is 0 and derivative of y square with respect to y is 2y. So in this case, x is treated as constant and we are differentiating with respect to y. So that's the reason the derivative of x square is 0 and derivative of y square is 2y, using the formula derivative of x power n is n times x power n minus 1. So with the help of this property, we can get this partial derivative. So basically, while solving the problem of partial derivative, we are using the identity of differentiation only. The identities of differentiation will remain same. The only important result here is if we are differentiating with respect to one of the variable, we are treating other variable as a constant. Okay, so this is the definition of partial derivative of a function at a point. Otherwise, this is the definition of the partial derivative. Means if we are differentiating with respect to one of the variable, we are treating other variable as a constant. Okay, now we move to the condition of the differentiability of the function. Differentiability. When we say that a function is a differentiable at a point. So firstly, we should know that what is the total derivative. Firstly, we'll discuss the condition of for the differentiability of the function. So there are two conditions. The first one is the necessary condition, which is this is the necessary condition. So suppose that I want to say the differentiability of the function z equal to f of x y, say at a point x naught y naught. Okay. So what is the first condition? That is the necessary condition. The necessary condition is the existence of the partial derivative, existence of the partial derivative at a point x naught y naught is the necessary condition. Is the necessary condition for the differentiability of the function. That means curly f upon curly x at the point x naught y naught and curly f upon curly y at the point x naught y naught should exist. X naught y naught should exist. Okay. The second one is the sufficient condition. Second one is the sufficient condition. The sufficient condition is if the partial derivatives are continuous. If the partial derivatives curly f upon curly x at the point x naught y naught and curly f upon curly y at the point x naught y naught are continuous. Okay, if the partial derivatives, okay, just wait a moment. I can write here that if the partial derivatives are continuous at the point x naught y naught, at the point x naught y naught, then your function f of x y is a differentiable at the point x naught y naught. Okay, so it means that if the partial derivatives exist, this is the necessary condition. If the partial derivatives are continuous also, then your function is definitely differentiable. So we can say here we get two important points. Means if partial derivatives does not exist, if curly f upon curly x at the point x naught y naught or and curly f upon curly y at the point x naught y naught. If they does not exist, then your function is not differentiable. F of x y is not differentiable. Okay, and this is the sufficient condition. Sufficient condition means that if the partial derivatives, if the partial derivative curly f upon curly x and curly f upon curly y, they are not continuous. They are not continuous. Even then your function may be differentiable. So it means that your function f of xy may or may not be differentiable. May or may not be differentiable. Okay, so basically we have a two condition. If the partial derivative does not exist, your function is not differentiable. If the partial derivative exists and are continuous, then your function is differentiable. But if the partial derivative exists, but partial derivatives are not continuous, your function may or may not be differentiable, right? So basically there we need to come up with one condition with the help of which we can directly conclude that your function is differentiable or not. So what is that condition? So this is the necessary and sufficient condition. You can say that with the help of this, we can conclude that your function is differentiable or not. So the condition for the differentiability is condition for the differentiability with the help of which we can conclude that your function is differentiable or not is limit delta rho tends to 0 delta z minus dz upon delta rho equal to 0 where delta z is equal to the incremental value of the function at the point x naught y naught. So basically this is f of x naught plus delta x y naught plus delta y minus f of x naught y naught And what is dz? Dz is basically the definition of total derivative, but because here we have applied limit, so we are considering its value in the incremental form. Then it is curly f upon curly x at the point x naught y naught delta x plus curly f upon curly y at the point x naught y naught delta y. Okay, and delta rho. Like I already told you that whenever we want to prove the limit of a function, we are considering the neighborhood of a point is the circle. So in this case, while proving the limit of the function, so we are assuming delta x equal to delta rho cos theta, delta y equal to delta rho sin theta, right? So delta x square plus delta y square, this is equal to delta rho square. So what is delta rho? This is basically square root of delta x square plus delta y square. So because delta x and delta y is a small increment value, so whenever we want to check the differentiability of the function, we need to apply the limit delta x and delta y approaches to 0, 0. So in this case, that limit now converted into limit delta rho tends to 0. So what is delta rho here? It is delta x square plus delta y square, right? So in this case, how do we conclude that your function is differentiable at a point or not? If this limit exists and is equal to 0, then we say that your function is differentiable at the point x naught, y naught. And if this limit does not exist or this limit is not equal to 0, then we can say that your function is not differentiable at a point. Okay. Now, let us consider one problem on the basis of the differentiability of the function, and then we'll discuss some problem based on partial derivatives also. Right? Suppose the question is check the differentiability of the function. Check the differentiability of the function f of x y equal to square root of x square plus y square at the point 0, 0. Okay, so we want to check the differentiability of the function at the point 0, 0. Okay, so now what we have discussed while to check the differentiability of the function. So here, even if you check here, like with the help of this condition, we can check the differentiability because in this particular case, it may be possible that the partial derivatives are not continuous, but your function is differentiable. So basically, with the help of this condition only, we can conclude that your function is differentiable or not. But even for this particular part, we need firstly the partial derivative of the function at the point x naught, y naught, right? So that's the reason here. This is the necessary condition. The existence of partial derivative is the necessary condition for the differentiability of the function. Okay. So the first step is we need to find out the partial derivative of the function at the point x naught, y naught. So firstly, we are going to apply the definition curly f upon curly x at the point 0, 0. So what is the definition of the partial derivative at a point? So this is the definition of the partial derivative of the function at the point AB. So if we use here, this is equal to limit delta x tends to 0, f of 0 plus delta x 0 minus f of 0, 0 upon delta x, right? Because curly f upon curly x at the point AB, right? So we have discussed this formula that this is limit delta x tends to 0, f of a plus delta x b minus f of ab upon delta x. So because we want to find out partial derivative with respect to x, so we are making variation in x variable only and y variable is treated as constant. So here a is 0 and b is 0. So we are using this particular formula. So here your function f of xy is, here your function f of xy is square root of x square plus y square, right? So what is f of 0, 0? So if I replace x equal to 0 and y equal to 0, then its value is 0 only, right? And one more thing. So here basically your function is f of 0 plus delta x means Here your function means this is limit delta x tends to 0, f of delta x 0 minus f of 0 0 upon delta x. But f of 0 0 is already 0. And what is f of delta x? It means that I'm going to replace x with delta x and y with 0. So this is equal to limit delta x tends to 0, square root of delta x square minus 0 upon delta x. Now, one important result we are using here. The result is that the square root of a number is always positive, right? So, but when I say that delta x, here delta x tends to 0 means delta x maybe tends to 0 from positive side or from negative side. So that's the result. When we are saying that the square root of a number is always positive. So what is the square root of x square? It is mod of x because mod of a number is always positive. So in this case, what is the limit of this function? This is limit delta x tends to 0. So square root of delta x square become mod of delta x upon delta x. This is the value of curly f upon curly x at the point 0, 0. Now, what will happen in this case? So we know that delta modulus function is basically defined in this way that mod of x is equal to x if x is greater than or equal to 0 and its value is minus x if x is less than 0. So if we are using this concept here, so what do we get? That limit delta x tends to 0 from positive. If I am applying 0 from positive side, then mod of delta x upon delta x, this is limit delta x tends to 0 from positive. And if it is positive, it is from the positive side, then mod of x is equal to x only. Its value is delta x upon delta x cancel out, so its limit comes out to be 1, right? But on the other hand, if I am considering limit delta x tends to 0 from negative mod of delta x upon delta x, then modulus function is defined as its value is minus x if x is less than 0, right? Because we know that what is mod of minus 7? It is 7. But how minus 7 becomes 7? We are basically multiplying minus sign with minus 7 to make it positive, right? So if the number is negative, then the value of modulus is negative of that number so that the outcome is positive. So it means that its value comes out to be minus of delta x upon delta x. So delta x get cancelled out. So its limit comes out to be minus 1. So it means that its limit is either plus 1 or minus 1. So because the limit is not unique, it means limit does not exist. So what does it mean? So because limit does not exist, it means that curly f upon curly x at the point 0, 0 does not exist. Does not exist. So if the partial derivative does not exist, because this is the necessary condition for the differentiability of the function. This is the necessary condition for the differentiability of the function. Because the partial derivative does not exist, hence we can conclude that f of xy, that is square root of xk plus ysk, is not differentiable at the point 0, 0. Is not differentiable at the point 0, 0. Okay. Okay, so this is one of the problem here. Now let us consider the another one. Another question is now this time we want to check the differentiability of the function. Check the differentiability of the function f of xy, which is defined as x square plus y square into cos of 1 upon square root of x square plus y square when xy is not equal to 0, 0 and its value is 0 when xy is equal to 0, 0. So we want to check the differentiability of the function at the point 0, 0. So In this case, again, I want to check the differentiability of the function at the point 0, 0. So the first condition is the necessary condition. So for the necessary condition, what can we do? We firstly calculate the partial derivative of the function at the point 0, 0. So again, we are using the definition here. This is equal to limit delta x tends to 0, f of 0 plus delta x 0 minus f of 0, 0 upon delta x. So this is equal to limit delta x tends to 0, f of delta x 0 minus f of 0, 0. Now in this case, your function is already defined at the point 0, 0, and the value of the function at the point 0, 0 is 0 upon delta x, right? And when x, y, both of them are not 0, then this is how your function is defined. So it means that when f of delta x 0 means that we are going to put here x equal to delta x and y equal to 0. So this is equal to limit delta y tends to 0. This becomes delta x square, y becomes 0 into cos of 1 upon square root of delta x square minus 0 as it is there and divided by delta x. So here one of the power of delta x get cancelled out with this, and already we have discussed that the square root of a number is always positive. So this is equal to delta x into cos of 1 upon mod of delta x. Now here it is a product of two functions. Now because limit delta x tends to 0, into we have a cosine function, and we know that cosine function is a bounded function, that cos theta its value always lies between -1 and 1. So because cosine is a bounded function, and if you multiply 0 with a bounded function, 0 into a bounded function into a bounded function, whose value lies between -1 and 1. So when I multiply 0 with a bounded function, then the value comes out to 0, right? So what does it mean? It means that curly f upon curly x at the point 0, 0, its value is 0. So this is the partial derivative of the function with respect to x. Now similarly, we can find out partial derivative with respect to y also. So what is curly f upon curly y at the point 0, 0? This is equal to limit delta y tends to 0, f of 0 plus delta y 0 minus f of, sorry, delta y means that we are making variation in y coordinate, right? So this is f of 0, 0 plus delta y minus f of 0, 0 upon delta y. So this is equal to limit delta y tends to 0, f of 0 delta y minus f of 0, 0 upon delta y. Again, your function is defined that when xy is equal to 0, 0, the value of the function is 0, right? And otherwise its value is this one. So if we substitute its value here, then this is limit delta y tends to 0. This is delta y square into cos of 1 upon square root of delta y square, and f of 0, 0 is 0 upon delta y. Or this is equal to limit delta y tends to 0, delta y square into cos of 1 upon mod of delta y. Like we have discussed that the square root of a number is always positive, divided by delta y. So one power of delta y get cancelled out with this. So it means that we left with limit delta y tends to 0, delta y into cos of 1 upon mod of delta y. Again, same result, that delta y is tends to 0. So 0 into a bounded function, 0 into a bounded function whose value lies between -1 and 1. So if you multiply 0 with a bounded function, its limit comes out to be 0. So what does that mean? Curly f upon curly y at the point 0, 0 is 0. So it means that partial derivative exists. Curly f upon curly x, curly f upon curly y both exist at the point 0, 0. So now we want to check the differentiability of the function. So there are basically two different conditions for the differentiability of the function. The first one is, of course, partial derivatives should exist. So if the partial derivatives are continuous, then we say that your function is differentiable. But if your partial derivatives are not continuous, even then your function is differentiable. So in that case, we can check this condition, right? So what can we do? Firstly, we'll try to check the condition for the differentiability, right? So firstly, we'll try to check the differentiability condition with the help of this one, because with the help of this thing, we can conclude that your function is differentiable or not. Okay, later on we will check the condition of continuity also, because from that we can conclude that either it satisfies the condition for the continuity or not, right? So let us firstly check the condition. Limit delta rho tends to 0, delta z minus dz upon delta rho equal to 0. Now I want to check firstly this condition. Okay, so for this condition, firstly I need to check delta z. What is delta z? This is f of 0 plus delta x, 0 plus delta y minus f of 0, 0, right? So here we have already defined what is delta z. Delta z is incremental value in x and y coordinate at the point x naught, y naught, right? So here x naught, y naught is 0, 0. So this is equal to f of delta x, delta y minus f of 0, 0. So as our function is defined, this is equal to delta x square plus delta y square into cos of 1 upon square root of delta x square plus delta y square. And f of 0, 0 is 0. So its value is delta x square plus delta y square into cos of 1 upon square root of delta x square plus delta y square. Now, what is dz? Now, what is dz? dz is curly f upon curly x at the point x naught, y naught, which is 0, 0 times delta x, curly f upon curly y at the point x naught, y naught, delta y. Basically, this is a definition of total derivative. And we have already calculated partial derivative at the point 0, 0, its value comes out to be 0, 0 only. So it means that this is 0 into delta x, 0 into delta y. So it means that its value is 0. So dz is 0. So therefore, and what is delta rho? The delta rho is square root of delta x square plus delta y square. Okay, so if I consider limit delta rho tends to 0, delta z minus dz upon delta rho. This is equal to limit delta rho tends to 0. Delta z, its value is delta x square plus delta y square into cos of 1 upon square root of delta x square plus delta y square minus dz. dz is 0 on delta rho. Also, delta x square plus delta y square. This is delta rho square, but because this is how we have defined the delta rho. So this is delta rho square into cos of 1 upon delta rho upon delta rho. Again, one power of delta rho get cancelled out. And again, because delta rho tends to 0, so it is 0 into a bounded function, so its limit comes out to be 0. Okay, so hence this condition is satisfied. So because this condition is satisfied, so we can conclude that your function f of xy is differentiable at the point 0, 0. So your function is differentiable at the point 0, 0. So here we have proved this particular thing, right? So it because this condition satisfied, so it means that your function is differentiable. Now we have discussed one more thing, like here we have another condition also. If your partial derivative exists and they are continuous also, then your function is also differentiable. Let us try to check the condition of continuity also. So what is the condition of continuity? The condition of continuity of the partial derivative at the point 0, 0 is if the limiting value of the function is equal to the value of the function at that point, then we say that your function is continuous at the point. Okay. So basically, I want to prove that the value of the function at the point 0, 0, it is equal to the limiting value of the function at the point 0, 0. Okay. So firstly, in this case, I am directly find out the value of the function at the point curly f upon curly x, and then we apply the limit here. Okay. So what is your function? Let me rewrite here. Our function f of xy is defined as xk plus ysk into cos of 1 upon square root of xk plus ysk when xy is not equal to 0, 0 and its value is 0 when xy is equal to 0, 0. So in this case, because I want to find out the limiting value means your function is not x and y, they are not equal to 0, 0. Okay. So basically, I need to differentiate my function in the neighborhood of a point 0, 0. Okay. So let us differentiate this function with respect to x. So I'm considering my function f of x y as x square plus y square into cos of 1 upon square root of x square plus y square. This function I'm going to differentiate it with respect to x directly. Okay, so now I'm going to differentiate my function. So for the differentiation, like I told you, here we are going to use the concept that if we are differentiating with respect to x, we are treating y as a constant. So curly f upon curly x. So basically, both the function they depend upon x. So here we are going to apply the product rule. So what is the derivative of u and v? So I'm going to use some property here. I'm going to write these properties side by side. So what is the derivative of the product of two function f and g? So this is first function derivative of second plus second function derivative of first. So firstly, I'm going to use this property here. So it is equal to first function x square plus y square into derivative of second curly by curly x of cos of 1 upon square root of x square plus y square plus cos of 1 upon square root of x square plus y square into curly by curly x of x square plus y square. Okay, so here we have applied this formula product of f into g, f derivative of g plus g derivative of f. Now, if we talk about the partial derivative of x square plus y square, we already know that if we are differentiating with respect to x, we are treating y as a constant. So curly by curly f x of x square, curly by curly x of y square. So derivative of x square is 2x using the property that d by dx of x raised to power n is n a time x raised to power n minus 1, and derivative of y square with respect to x is 0 using derivative of constant is equal to 0, because when we are differentiating with respect to x, we are treating y as a constant, right? So what does it mean? That curly by curly x of x square plus y square, this is equal to 2x. Okay, so it means that we'll get the value of this particular part. Now come to this one. Now what will happen in this case? So basically, if you just look at here, it is a composition of the function. So in case of composition of the function, we need to apply chain rule. So it is like f of g of xy. It is like f of g of xy. So if I want to differentiate my function, composition of the function with respect to x. So in this case, what we need to do, we need to apply here chain. So your function depend upon g of xy. So we are considering it as a single function. So in this case, chain rule, if your function is a composition of the function, firstly I'm going to differentiate f. So what is the derivative of f? It is f dash. What is the derivative of f? It is f dash. Is I'm going to differentiate my function with respect to g of xy. And then with the help of chain rule, because g directly depend upon x and y, and I need to differentiate it with respect to x. So we are going to differentiate partially with respect to xy. We are going to differentiate g of xy with respect to x. Okay. So, so if I need to apply the composition, firstly, what is the derivative of cos x? Derivative of, because it is a cosine. So here what is f? F is cosine, and what is g of xy? It is 1 upon square root of x square plus y square. Basically, 1 upon square root of x square plus y square is again a composition of the function. It is again of the form f of g of xy, because 1 upon square root of x square plus y square means x square plus y square, right? Like, firstly, let me write derivative cos x is minus sin x, and derivative of 1 upon square root of x. This means derivative of x raised to the power minus 1 by 2. And derivative x raised to the power minus 1 by 2 minus 1 by 2 x raised to the power minus 3 by 2. Using power, this one. Okay. So basically here, cos is again a composition of the function, and this is again composition of the function. 1 upon square root of x square plus y square means it is a composition of your function f is 1 upon square root of x, and g of xy is x square plus y square. Okay. So we are going to use these two formula here. So what do we get? So this is equal to x square plus y square. Now using chain rule, the derivative cos is minus sine of 1 upon x square plus y square. So we are using derivative of chain rule. Okay. Derivative of f of g of xy is f dash. Now again it is a composition of the function. So derivative into curly by curly x of x square plus y square raised to the power minus 1 by 2. And here this is 2x times cos of 1 upon square root of x square plus y square. Right? And now I'm going to differentiate this function again. Again, it is a composition of the function f of g of xy. So if I again differentiate this, what do we get? This is equal to x square plus y square into minus, I'm taking this side, sine of 1 upon square root of x square plus y square, and derivative of this function is minus 1 by 2 x square plus y square raised to the power minus 3 by 2 into partial derivative of x square plus y square, and partial derivative of x square plus y square is 2x. Okay, plus 2x times cos of 1 upon square root of x square plus y square. Okay, so here this 2 and 2 get cancelled out. Here this negative sign also get cancelled out with this negative sign. So here the power of x square plus y square is 1. Here the power of x square plus y square is minus 3 by 2. So 1 minus 3 by 2 is minus 1 by 2. Okay, so if I write this, so what do we get? So curly f upon curly x is equal to x square plus y square raised to the power 1 minus 3 by 2, right, into x into sine of sine of 1 upon square root of x square plus y square plus 2x times cos of 1 upon square root of x square plus y square. So this will gives us, it is minus 1 by 2, so it is x upon square root of x square plus y square into sine of 1 upon square root of x square plus y square plus 2x times cos of 1 upon square root of x square plus y square. So this is curly f upon curly x, right? Now we want to check the continuity of the function. So firstly, I'm going to apply the limit. So limit xy tends to 0, 0, curly f upon curly x. So this is equal to limit xy approaches to 0, 0, x upon square root of x square plus y square into sine of 1 upon square root of x square plus y square plus 2x into cos of 1 upon square root of x square plus y square. Okay, now because I need to evaluate the limit of this function, and I told you whenever we have a function 1 upon x square plus y square or x square plus y square is there, then preferably we convert it into polar form. So because with the help of the polar form, we get, if the limit of the function exists, then we can get the unique value of the limit. And if the limit depend upon theta, then we say that limit of the function does not exist, right? So let us substitute here. Let us transform x to r cos theta, y equal to r sin theta. So x square plus y square is equal to r square. And as xy approaches to 0, 0, it implies that r approaches to 0. Okay, because we are considering the neighborhood of a point 0, 0 is a circle whose radius is r. So as any point xy approaches to this point 0, 0, it means that this radius approaches to 0. Okay. So if we use this transformation, then this problem now limit xy approaches to 0, 0, curly f upon curly x. Now it is transformed to limit r tends to 0, x is r cos theta upon, because x square plus y square is r square, so its root is, radius of a circle is always positive, so its value is r sine of 1 upon r 2 times r cos theta into cos of 1 upon r. So here r and r get cancelled out. So we have a cos theta limit r tends to 0 sine 1 upon r plus cos theta limit r tends to 0 r into cos 1 upon r. Now r tends to 0, cosine is a bounded function. So this limit is 0. 0 into cos theta is 0. But here limit r tends to 0 sine 1 upon r. Now, although we know that sine is a bounded function, but limit r tends to 0 sine 1 upon r does not exist. This limit does not exist. Okay, because function 1 upon r tends to 0 does not exist. So is the limit of sine 1 upon r. So because this limit does not exist, so because limit r tends to 0 sine 1 upon r does not exist. So it means that limit xy tends to 0, 0, curly f upon curly x does not exist. So because limit does not exist, so obviously there is no question about continuity. Hence, curly f upon curly x is discontinuous at the point 0, 0. So what does it mean? So in this question, we have concluded that the function, the partial derivative of this function exists, and your function is also differentiable at the point 0, 0, because the differentiability condition is satisfied. But here we have also proved that the partial derivatives are discontinuous. So it means that here we have actually proves this particular condition that even partial derivatives are not continuous, your function may be differentiable, right? Okay, so if the partial derivatives are continuous, then your function is definitely differentiable. But if the partial derivatives are not continuous, even then your function may be differentiable. So that's the reason. If we want to check the condition of differentiability of the function, in that case, we have to use this particular condition. Okay. Okay, so in this video, we have focused on the problem of the differentiability of the function only. So in the next video, we'll try to discuss some problem based on the partial derivative of the function. Okay, how do we calculate the partial derivative of the function? at a point, as well as we'll discuss the changes. Okay, so I think that is enough for this particular part. So I'm expecting you just try to revise the problem based on the differentiability of the function. If you find out any doubt or any query related to that, then you can post your query in the comment section. I'll try to provide you the solution of the same. So thank you. Have a nice day.